Hi there, so this video is section 4.5, which is the last section in chapter 4, and we are going to be looking at another method of integration, so adding to our integration toolbox, and this is integration by substitution, which is also known as performing U substitution. So if we look at any of these integrals, indefinite integrals, we don't yet know with the tools that are currently in our toolbox, right, which are just power rule for integration, and then just for trig functions, the one integrating the trig functions that follow the reverse of differentiation. So at this point, we cannot integrate these functions, but we will be able to using U substitution. So the idea behind integrating by substitution is that you are rewriting a function or an integral in a simpler form that's in terms of U. And this only works whenever you have a function that is f composed with g times g prime, where we end up rewriting f of g of x as f of u, so in terms of u, and then g prime dx ends up being replaced with du. And we end up rewriting the integral in simpler terms in a way that you can integrate using those basic rules of integration. So in this case, u is equal to g of x. And we're going to talk about how we identify, because not all functions can be integrated by hand using the techniques that we've talked about. So this is just kind of adding another method to our toolbox, which will allow us to integrate more functions. So we're going to talk about how to identify what we want to let u equal to, and that's probably the toughest part about integrating using a u substitution, because sometimes it can be a little bit trial and error deciding what g of x is. So again, it's rewriting a function that's a composite function in terms of u. So in this case, for this function, which is the quantity x plus 2 cubed, this one's pretty straightforward. So this is going to be my side work over here, and I'm going to let u, and you have to do this step, Colin, you have to write this down. You have to let u equal to x plus 2. So I'm letting u equal to what's inside the parentheses here. And then after I do that, I'm going to think about differentiating u. So I'm focusing on this equation. I'm going to differentiate u with respect to x. And I write that as du over dx. And the derivative of u with respect to x, just thinking differentiation rules, is 1, right? The derivative of x is 1, derivative of 2 is 0. Well, notice I have decided to let x plus 2 equal to u, and now I'll be integrating u cubed, but this variable needs to match this variable. So we need to see what we can replace dx with. And notice that if I go to this equation, if I were to think about multiplying dx on each side, we end up with du is equal to, sorry, not du, du is equal to dx. So we're actually able to just replace the dx with du. So this integral is equal, based on my side work, to the integral u cubed du. And we do know how to integrate that. So then just applying power rule for integration, that'll be 1/4 u to the 4th, or that can be written as u to the 4th over 4 plus c. This is an indefinite integral. And then our last step is just going to be to substitute what we let u equal to back in. So 1/4, and then times the quantity x plus 2 to the 4th plus c. So that's what this indefinite integral is equal to. And you can always double check. So if you want to do a check, I'm not going to do this for each one, but I'm going to show you how you can. By saying, okay, well, the derivative of this, so the derivative of 1/4 times x plus 2 to the 4th, you're welcome to do a mental check as well, should be equal to this, right, to what we integrated. So if we think about taking the derivative, well, thinking chain rule for differentiation, right, that would be derivative of the outside. 1/4 times 4 is just 1. Subtract 1 from the exponent. Leave the inside alone. Times the derivative of the inside would just be times 1 in this case, so we don't have to write that. And then the derivative of c would be 0. So we can see that the derivative of our general antiderivative ended up matching, in this case, the quantity x plus 2 cubed. So that was just a check. This, again, this is side work. So make sure it's off to the side. Make sure it is not equal. I will take off points if you try and put that inside the steps here. It should be off to the side, what you're letting u equal to. Okay, so let's try another one. And if you want, you can always pause the video, try the problem on your own, and then double check that it's the same thing that I got. Okay, so we want to see what we want to let u equal to. Okay, and this is 6x squared times the square root of x cubed minus 1. Now remember, back up here, our definition, that we want to replace g prime dx with du. Okay, so we want to pick to let u equal to g of x, where its derivative will be left in the function, and then we'll be able to replace that derivative dx with du. Okay, so to do this, why don't we think, I see x cubed minus 1 is underneath that square root. So let u equal to x cubed minus 1, and the reason I'm saying that is because, well, I don't know how to integrate what the square root of x cubed minus 1. But also there's an x squared left there. So I know that when I take du over dx, right, the derivative of u with respect to x, that's 3x squared. And if we solve for dx, so if we think about multiplying by dx on each side here, right, we would have dx, 3x squared, or sorry, du equals to 3x squared dx. Notice that 2 times 3 is the same as 6. So notice that I can let du equal to the 3x squared dx, and I'll still have a 2 left in there. So that's one option, to just go directly to saying that this would be equal to the integral of 2 root u du. If you recognize that, that's less steps. But if you do not recognize that, or you don't want to think about it, that's okay too. You can always solve for dx. We'd get du over 3x squared. And then we've let u, we still have 6x squared, but we've let u equal to x cubed minus 1. So this will be the square root of u. And then we can just replace the dx with du over 3x squared. And we still have x's here, but notice that the x squareds will cancel, and then 6 divided by 3 is 2. And we can pull that 2 out. And then that's u to the 1/2 du. And then that's something we know how to integrate just using power rule. So 2 times 1 over 1/2 plus 1 will be 3/2 u to the 3/2 plus c. And I want to think about simplifying that. So that'll end up being, when I multiply by 2, 4/3. And then in this step, I also want to replace what I let u equal to. And we're done. You could always double check by thinking about taking the derivative of that. Okay, again, my side work is over here. Before you rewrite, you have to state what you are letting u equal to. Okay, rational function. So rational function, you're usually going to let u equal to either the numerator or the denominator. Oh gosh, you guys don't know how to integrate this yet. Well, I'm just going to show you it, but in chapter 5, we'll learn how to finish integrating this. But for now, I'll just go with it. Okay, so we're actually going to let u equal to 2t squared plus 5 du over dt would be 4t. And then if you're solving for dt, you'd get du over 4t equals to dt. You could also recognize what t dt would be equal to, which would be du over 4. It's just one less step to do. So we'll have the integral of t, the way that I have it written right now, t over u, and then du over 4t. Okay, the t's will cancel, which we need to happen because we need everything in terms of u before we can integrate. So notice that this leaves us with the integral of 1 over u du. Well, 1 over u is the same as u to the negative first. And u to the negative first, when we first in 4.1 talked about power rule for integration, we cannot use power rule here, right? Because we would end up with 0 in the denominator, right? Because we'd have u to the negative first. So then, yes, so then you would have 1 over negative 1 plus 1, which would be 1 over 0, and that doesn't work. So I'm going to tell you or show you, where'd the 4 go? I still need the 4. So 1 over 4u, which is the same as 1/4 on the outside. I can pull the 1/4 outside of the integral. So this will end up being 1/4 times the integral of 1 over u, which we're going to talk about in chapter 5, is actually the natural log of the absolute value of u plus c. And then substituting the u back in, and again, we will go over the integral of 1 over u being natural log of absolute value of u. We will go over that in chapter 5. That's not something I'm expecting you to know yet. Okay. And again, if you want to, this is one you could do. So if you would like to pause the video and try it on your own and then make sure that your work matches mine. Okay, so let's let u equal to 1 minus 4x. So du over dx will be negative 4. So du over negative 4 is dx. So we'll have the cube root of u, which is the same as u to the 1/3. And then I'm replacing dx with du over -4. So I can pull the -1/4 out, and then I'm thinking about integrating using power rule, u to the 1/3. So 1 over 1/3 plus 1, u to the 1/3 plus 1 plus c. Okay, so that would be -1/4. And then that ends up being 1 over 4/3, so 3/4. So -3 over 16 u to the 4/3 plus c. And then finishing by substituting the 1 minus 4x back in for u. Okay, side work over here. Okay. So integrating, there's a trig function in there. Let's let u equal to 3x squared minus 2. And it's usually like the inside of the composite function is pretty obvious. But also you're thinking, well, will the derivative be left? Like 4x, the derivative of x squared is x. So we know that when we take the derivative of u with respect to x, we're going to have something left that will cancel. So that's 6x. So solving for dx, we get du over 6x equals to dx. Okay, so this equals to, we still have 4x there, cosine of u, I use parentheses, cosine of u, and then I'm replacing dx with du over 6x. The x's will cancel. And then for 6, this 2/3. So that'll be 2/3. The integral of cosine is sine. Sine of u plus c. And then just replacing what I had let u equal to back in. Okay. Again, if you would like to pause, this one you can do. Let's let u, and I feel like at first, students, when they first start u substitution, they first want to let u equal to that whole denominator. The thing is, the derivative of that whole denominator is going to be pretty complicated, and you would only have the 9x squared left. So instead, let's let u equal to x cubed plus 4. So du over dx would be 3x squared. Solving for dx, we will have the integral of 9x squared we haven't touched yet over u to the 6th. And then we are able to replace dx with du over 3x squared. Now this is another one where you could have recognized the 3x squared dx would be replaced with du. That would have been one less step. Or if you just want to think about solving for dx, that's fine too. So x squareds cancel. 9 divided by 3 is 3. So this ends up being 3 times u to the -6th du. So we can use power rule. That'll be 1 over negative 5u to the negative 5th plus c. So negative 3/5, or I'm just going to write this as a single fraction. So negative 3 over 5 times x cubed plus 4 to the 5th plus c. Okay, and did we redo this one? No, we just did one that was very similar to it. Okay, why don't you try this one on your own? Okay, hint, let u equal to x cubed plus 1, and then go from there. Okay, now, like I said at the beginning of the video, u substitution doesn't always work. So just because you can't use power rule doesn't mean that u substitution is going to work. So this is an example where the integral of x squared plus 4 to the 7th power. Now this is a polynomial function. In the way that it's written, it looks like you could potentially use a u substitution. Like we would want to let u equal to x squared plus 4, but it's not going to work. And then du over dx is equal to 2x, and you try and solve for dx. And then when you go to rewrite the integral, you're like, okay, I have the integral of u to the 7th, but when we replace dx, it's du over 2x. And we can't get that x to cancel. It's stuck there. And we can't integrate when we still have x in the integral. So it does not work, fail. Now, this function could actually be integrated. You would just have to expand that. You'd have to multiply out x squared plus 4 times itself 7 times, and nobody has time for that. There are other ways that you could expand. There are shortcuts, but that's another lesson. Okay, so u substitution is useful for the argument of a trig function, the exponent of an exponential function, which will be chapter 5, a denominator or a numerator. This is what I'm saying you can let u equal to is often the argument of a trig function, the exponent in an exponential function, a denominator, a numerator, or an expression that's under a radical sign. And again, it's important to remember not all functions can be integrated with the rules we're familiar with. Now, these were all indefinite integrals. What about definite integrals? And you integrate them using the same method, like you're rewriting the integral in a simpler form in terms of u. The thing is, you have to do something with those limits of integration. So you have to find, when you rewrite the integral, you have to find the new limits of integration. Okay, so just focusing on x over the square root of x squared plus 4, let's figure out what we're going to let u equal to. Let's let u equal to x squared plus 4, okay? And before we do anything, let's find our new, where do I want to write this? Let's find our new lower limit of integration, and we find that by substituting the lower limit of integration, which is 0, into what we let u equal to. So 0 squared plus 4 equals to 4. Okay, so that'll be our new lower limit, our new upper limit of integration. We're going to substitute 2 in to what we let u equal to. So that'll be 2 squared plus 4 will be 8. Okay, and then same side work as before. Du over dx is 2x. So if we go to solve for dx, we'll have du over 2x equals to dx. Okay, so our integral will now be from 4 to 8. And I like to label them as I'm writing them out just to remind me what is what. And then we still have x in the numerator. The denominator is going to be the square root of u. And when we replace dx, we have du over 2x. So those x's will cancel. And then I'm going to pull the 1/2 out and rewrite that as u to the negative 1/2 power du. And now it's just integrating and applying the fundamental theorem of calculus. So the 1/2 is going to hang out here. This is where I like to use the bracket notation when I apply fundamental theorem of calculus. So that'll be 1 over negative 1/2 plus 1, u to the negative 1/2 plus 1. We don't need plus c. Write down our limits of integration. And I'm going to do one extra step of simplifying here. So that'll be 1 divided by 1/2, which is just 2. So u to the 1/2. And then now we can apply fundamental theorem of calculus. So 1/2 is going to hang out. That'll be 2 times 8 to the 1/2, or the square root of 8, minus 2 times the square root of 4, right? F of b minus f of a. And notice that if we distribute the 1/2 back in, that the 2's will cancel. So that leaves us with the square root of 8 minus 2, or 2 root 2 minus 2, if you simplify the square root of 8. And you could always double check that with using your calculator. So again, this is all side work. Get a nice box there. Okay, so that's side work. And so the only difference with applying the u substitution for the definite integrals is that you have to remember to find the new lower and upper limit of integration. Now you can technically avoid that if you basically first think about integrating the indefinite integral, and then you apply the fundamental theorem of calculus with what you've already resubstituted, what you let u equal to back in, and you can use your old limits. But I think it's a lot to remember, so I think it's better to just find the new limits. Did I give us another one? I give us another one where you guys aren't going. Well, I guess I showed you, so we can't do it, but you need chapter 5 for this. Okay, so let's let u equal to the denominator, because notice that the denominator, when we take the derivative, would end up canceling with the numerator. So we'll have u equal to x squared plus 4x minus 3. Let's find our new, I'm going to call it LL, lower limit. And we find that new lower limit by plugging 1 in for what we let u equal to. So we get 2, and then our new upper limit is 18. So du over dx is 2x plus 4. And if you solve for dx, you get du over 2, which I'm going to rewrite that as 2 times x plus 2, the quantity x plus 2. So that when I come back over to rewrite the integral, which is now going to be from 2 to 18, that x plus 2, I can see, will cancel with the x plus 2 that's in the denominator here, right? This will cancel with this. So then we are left with, I'm going to pull 1/2 out, with integrating 1 over u, which I've told you already is natural log of absolute value of u. And then applying fundamental theorem of calculus, that'll be ln of 18. I don't need the absolute value bar since 18 is positive, minus ln of 2. We could leave it there. I mean, we could use properties of logarithms and rewrite this as what that could be 1/2 times ln of 18 divided by 2, or ln of 9, 1/2 ln of 9. If you were hung up on how I just simplified that, we will kind of briefly review properties of logarithms at the beginning of chapter 5, so don't worry about it. Don't worry about it yet. I'm not going to expect you in chapter 4 to be integrating 1 over u or dealing with logarithms. Sorry about that. I should have vetted my examples better. I used them from when I taught calculus before, and we went in a little bit different of an order. Okay, and is this the last example? I think this is the last example. This one we can do, so if you would like to pause the video, go ahead, and then you can double check after. Let's let u equal to what's being squared, so 2x squared minus 4x plus 1. Our new lower limit will be -1, and our new upper limit will be +1. Okay, and then du over dx is 4x minus 4. And you can either right away recognize what you're letting du equal to, or if we solve for dx, that's going to be du over 4 times the quantity x minus 1. So remember to put in your new limits of integration. So -1 to 1. The x minus 1 was still there. U squared, and then du over 4 times the quantity x minus 1. So those x minus 1s will cancel. We can pull 1/4 out. Okay, so then that'll be 1/3. So you can either leave the 1/4 pulled out, or if you didn't want to, you didn't have to, right? Because then when you think about integrating, So if you do it this way, you would leave the 1/4 out, and then you would think about integrating just u squared. So it would be 1/3 u cubed and you would leave 1/4 factored out times f of b minus f of a when you apply fundamental theorem of calculus. Okay, so that'll end up being 1/3 minus negative 1/3. So 1/4 times 2/3. Which will be 1/6. Okay, and side work is over here. Okie dokie, so that's integration by substitution method.